Hey guys, welcome back. So this is the last part of the law of thermodynamics lecture. It's one more topic. Then we're going to have some sample questions, and then we're going to do some in-class questions, and that's the end of this topic. We then have two more topics for this term, entropy and free energy. As of the time of this recording, you still have exam 2 to take, you still have the final to take, and the lab final is still there, and exam 3. So we don't have a lot of things out of the way yet. I know I still owe you some grading for your labs. That will get done this weekend. Today is the 9th, so hopefully that won't be too bad. But let's get talking about phase change. So we know what a phase change is. We've talked about phase change, going from solid to liquid, liquid to gas. We've talked about that. We've also talked about going for sublimation, which is directly from solid to gas. Okay, so those are the kinds of things that we're going to be talking about. Now, in 110, I talked to my students about temperature versus energy. And this is a plot that we have. And we know that this comes up, it plateaus, it comes up, it plateaus. And the reason that it does what it does is because we can heat that solid until it starts to melt. And then it stays there until it's all melted. And then we heat the liquid. And then it goes to that phase change to go to gas. And it stays at that temperature until all of it is gas. And then we can raise the temperature again. Okay? So this right here is associated with, no, not fusion, that's vaporization. The energy that it takes to vaporize, and this is associated with the energy that it takes to to fuse. So it's delta H fuse. Okay. So those are the quantities that we're talking about there. Now, what we're talking about is the molar heat of vaporization and boiling point. So delta H vape. Okay, that's the energy required to vaporize 1 mole of a liquid. We also have the molar heat of fusion and the melting point, the delta H fuse, which is the energy required to melt 1 mole of a solid. Now, delta H vape is always bigger than delta H fuse. Okay. And if I know the value of delta H to go from a solid to a liquid, and if I know the delta H to go from a liquid to a gas, I should be able to add those together to get the energy that it would take to go from a solid directly to a gas. And I can. I can see that the delta H of sublimation is equal to the delta H fusion plus the delta H of vaporization. Okay, they're additive in the same way that we've talked about with other things. We can always do it in the opposite direction, so go from gas to liquid and liquid to solid. And of course, we can go from gas directly to solid. And so those are all the phase changes that we see. Now, when we do it in the opposite direction, they're the same magnitude, same size, different sign. Okay. And one of the other things that I want to talk about here is this thing right here. And it says that we can have the natural log of P, which is the vapor pressure, is equal to the negative delta H vape over R times 1 over T plus C. Now, T is temperature. Delta H vape is that heat of vaporization for 1 mole of material. And R is the gas constant. And what this will show, so the slope of that line is negative delta H vape over R. And so if my heat of vaporization is really, really high, I'm going to have a very high slope for that line. And so we can get an indication of what kind of intermolecular interactions there are for a particular molecule by plotting this, by looking at this type of plot. Okay, and this is one of the ways that we can talk about that. So we can see that higher intermolecular interactions are going to require more energy. So if I have hydrogen bonding, that's going to require more energy. If I have dipole-dipole interactions, it's going to require more energy than something that is without those intermolecular interactions. So that's what we're talking about there. Okay, that is just an interesting note for you. I don't think that there's any of that on the test. So, I'm sorry. So that is our phase changes. Now, questions? I hope not. Now, for reasons that are way beyond what we're talking about here, I've had to record this 8 million times today. So I'm going to stop here and I will go to my next recording where we'll talk about the sample problems in just a minute. Thanks, guys.